Okay, now we're going to talk about arc length of polar curve. So in other words, what arc length really means is as follows. Like when we talk about circle, we talk about circumference, but when we're talking about arc length, it's the same idea as the area, but arc length, we're only, let's say, interested in finding this region in red. So still we have our angles alpha and beta as follows, but we're only talking about the circumference or the outer, not inside. Inside would be basically your area. So it can be derived as the same formula how we derived our parametric and rectangular arc length equation. So here's our formula: arc length L equals integral from alpha through beta, where alpha and beta are angles, and remember we're in our polar system, so it's f of theta, the quantity getting squared, plus f prime of theta, the quantity getting squared, d theta. Now here are a couple of things I want you to remember, and it's very important. This is not the second derivative, this is the first derivative getting squared, and this is just the function, then it is getting squared. So here's our first example. Find the arc length of the following logarithmic spiral. So if you draw it, you're going to see it goes in loops and it's a logarithmic spiral, and you can use your technology or graphing calculator to graph r equals e raised to the theta over 6, where theta lies between negative 2 pi to positive 2 pi. So it's an easy problem here because we are given our bounds, so we don't have to worry about our limits of integration, which is negative 2 pi to positive 2 pi. Actually, I'll move it over here so it's easier for us to see. Square root of the function. Our function is, so if you think about this r is acting as a function of theta, right? So we talked about it in class, so this is the same thing, and this is basically r prime of theta. So it's basically r prime is the same thing as saying f prime of theta. So inside you'd have e of theta over 6, that quantity getting squared, plus, now if we talk about the derivative, so f of theta equals e to the theta over 6, f prime of theta would be the same thing, e to the u is e to the u, times, due to the chain rule, it's times theta over 6. The derivative of theta over 6 is just 1/6 due to the chain rule. So let's put 1/6 e to the theta over 6, the whole quantity getting squared, d theta. Now one really important property is when you talk about exponents, the exponents multiplies, they do not add. Very, very important in this step. So you'd have negative 2 pi to 2 pi square root of e to the, if you simplify that, that's theta over 3, 2 times 1/6, plus 1/6, that quantity getting squared is 1 over 36, e to the theta over 3 d theta. Now right here it does not look like it's integrable, but always our principle is do not get intimidated by the problem. You always want to clean it up by doing algebra and so on. So here if you think about u substitution, it doesn't work, but if you really think about it, e to the theta over 6, here is your e to the theta over 6, the arguments are the same, so they are like terms. But in order to add the like terms, I need to have the same denominator. So imagine a 1 underneath, so I need to times it by 36 over 36, or imaginary 1 here to make him the same denominator, which would be 36 plus 1, 37. So square root of 37 e to the theta over 3 all over 36, a value from negative 2 pi to positive 2 pi. Here's my arc length. Now notice square root of 37 over 6 is just a constant, and we can always rewrite them having the constants outside. just to make the problem less complicated. And square root of 36 is just a 6, so I will put 37 over 6 outside and e to the theta over 3, and also square root is the same meaning as saying 1/2 exponent. Now it looks pretty complicated if you think so, but if we multiply the exponents, it would be square root of 37 over 6 from negative 2 pi to positive 2 pi e to the theta over 6 d theta. Now integral, if you notice, integral of e to the u du is just e to the u plus c. So we need to tell what our u is here, and our u in this problem is theta over 6, so your du is just 1/6 d theta. So I would go ahead and put a 1/6 here to compensate for it. I'll put a 6 outside. Now if that's the case, it simplifies down to square root of 37 integral of e to the u du. Notice I'm not putting my bounds because those you can do your change of bounds, but do not put negative 2 pi to positive 2 pi. That would be technically wrong because we have it in u's. So e to the u is e to the u, so square root of 37 e to the u, our u is theta over 6 evaluated from negative 2 pi to positive 2 pi, which is square root of 37 using the fundamental term of calculus, e to the 2 pi over 6 minus e to the negative 2 pi over 6, which is square root of 37 e to the pi thirds, simplifying, minus e to the negative pi thirds. That's your exact area of the arc length.